Good morning, everyone. Okay, so I believe you should have received your midterm 2. If I have graded for those who submitted on Gradescope, and you should see your grading there. And for those of you who submits to me other than the Gradescope, and I send the email to you with your work graded. I just wanted to explain a little bit. There seems to be some confusion about what is your score. Because Gradescope, there's a rubric entered for each of the problems. So you can see the total score automatically adds up to 60. Also, for those of you who worked on all 3 problems, or maybe question 4, question 5, and question 6, you choose 2 out of 3. But if you worked on parts of another extra problem, I also entered the grade on Gradescope. That's why you see the score might be more than what you received on Blackboard. The total score will be the 5 questions. So you choose 2 problems out of those 3. So the total score should be 45 maximum, right? So if you get 26, maybe on Gradescope, but maybe 5 of that is on an extra problem that you did not choose to include, or on extra problem that if you worked on all 3 and didn't specify which one, I just choose the highest 2 for you, okay? So for the extra problem, you see maybe your Gradescope total score is higher, but for the percentage calculation, I chose 2 problems, right, out of the 3 and divided that by 45%. So that's why you may see a difference in your Gradescope score and your Blackboard score. So you should use your Blackboard score as your final score. Gradescope is just a way for me to do the grading. And the Gradescope score is a raw score out of the question, the 45. So that's why it's a raw score. In Blackboard, you should see a column telling you your total points, and there's another column tell you your raw percentage out of 45. And I also did some curving. So your final score would be used for your midterm 2 is the one that after the curve. So the only score that matters to you is what is the percentage after the curve. That's your final score I will use for your midterm 2. Okay, hopefully that clarifies some of the confusion you're having.
I still have a question, kind of.
Yeah.
Because I didn't work on, there was no extra problem, but my scores are still different.
Okay, for those of you I do see.
Same with me.
Okay.
I skipped one.
Okay, let me go back and to see what the problem was. All right, let me take a screenshot. Benjamin, and Madison, Nathan, Charles, Queen. And for those of you who still have that same issue, send me an email, okay? If you're not in the chat, send me an email. I'll make sure to correct it. Maybe there's something messed up in the roster. Okay, and all right. So the average for now is 65% after curve. But again, like you guys said, if there's some mess up in the roster, and I'll have to make sure and I'll update you on what's going on there, okay? But that's what we're sending right now. Okay, all right, so if you have more questions, send me an email. Make sure you remind me later, okay? All right, so let's take a look at the pre-lecture, which is on the vector potential. So we pretty much finished the vector potential discussion. Just wanted to talk a little bit about this pre-lecture that we just did, pre-flight. So if the arrow represents vector potential A, which one of these that you're certain there is a non-zero B inside this dash region? So how is B and A related? B is equal to what of A?
The curl.
Curl of A, very good. So this is really just asking whether this curl is non-zero, and you're certain it's non-zero, right? So let's look at them. To talk about A, I wanted to talk about D first. Okay, so this is one of the questions on your midterm 1. you look at the curl is in the phi hat direction, and look at the vector in the phi hat direction. So to evaluate whether something has a curl, right, using Stokes, is like you're looking at the circulation of this vector, whether this is 0 or not. So we have to choose our line to be in the same direction of your vector. So your dot product is easy to calculate. So in this case, you will choose your line actually as sort of a donut shape so that the lines are always parallel to your vectors. These two lines are perpendicular, so you don't have to worry about them. Right? So for example, if I choose to evaluate my curl this way, up this way. So the bottom and you can see that my DL is longer on the outer side, is shorter on the inner circle. At the same time, my vector is smaller on the outer rim, but bigger on the inner rim. So in this case, here you're not so sure. But if the vector happens to be one of S dependence and your circle is 2 pi S, right? The circumference of your circle is how long the curve is increasing with respect to S. So the two of them have this effect that happen to cancel out each other. So your line integration on the bottom and the top cancel out. So giving you still a 0 line integral. But if you're sure about this one of S dependence, now in this case, it doesn't really tell you how much is varying. So here you can say possibly 0 curl or non-zero curl. But without the one of S dependence, we don't know for sure. So D possibly no B field, but again, we don't really know how the lines are changing. And A, if you look at A, you can see similar patterns. The difference is these lines do not get smaller. So if you do the same line integration, you can be sure the line integral does not go away. So this one I can say for sure does not have a 0 curl. Okay. Now let's look at another one. So B is clearly looks like you have a divergence, but in terms of a curl, if you okay, so you can also use the paddle wheel strategy to see if the paddle wheel will change directions. In this case, it doesn't look like the paddle wheel will be able to rotate. It's really just much more of a divergence analogy. If you spread some salt dust, it's going to spread outward. Or if the line's pointing in, it's going to have a flux pointing in, but it doesn't have a curl. Okay, so this one seems to indicate a divergence, but not a curl. So for C, okay, let's look at a C. C is interesting. The interesting what is happening in the middle, right? Right here in the middle, if you put a paddle wheel in there, it's going to rotate clockwise. You can look at because also line integration is non-zero because you have this arrow flip direction. So your arrow is dot DL is always positive. Whereas if you move to the upper side or the lower side here, you're going to have 0 curl. So here, the paddle wheel will not rotate. Here you also have 0 curl. So non-zero curl only occurs in the middle. So it looks like there will be a non-zero B field, but only in the middle. So right here in the middle, you have a B. So this one, you know for sure, within this dash line, you have a non-zero B. What about, now if we look at C, let's look at F. F is the same as C, but you are now restricting your area. You want to look at only in the upper side. And you can see the upper side, you have 0 curl. You don't have any curl. So here you have curl of A is 0, so no B. Okay. And what about E? E is the dash is down here, and you can see that E is similar to A, but you simply are moving toward a different region. So in this region, it does look like it's possible the paddle wheel will be able to rotate again because your vector flip directions, your paddle wheel will rotate. So here again, you will have a non-zero. You will have a non-zero curl. So it's definitely you have a P is non-zero. Okay. All right, just wanted to follow up quickly on this pre-flight that you did. Now let's going to move on to a different topic. We are going to start topic chapter 4. So we're doing chapter 4 and 6 together. So we're doing electrostatics, we did magnetostatics, and chapter 4 are E&M, E field and B field in matter, not just in vacuum, but in materials. So there are a lot of similarity between these two topics. That's why we're doing them together so we can draw analogies between them. So we're going to start our discussion on polarization. So we have done a little bit of polarization, and you're familiar with the influence of external E field. The positive and negative charges are going to respond to the external field, and they're going to realign themselves. So inside the materials, right? So also we have looked at physical dipoles. So for example, you have a positive Q and a negative Q here with a D pointing from the negative to the positive. So this one has dipole moment. Remember the definition for a dipole moment for a dipole looks like this. If P is Q times D. Or in general, if you have a lot of charges, then you can calculate your P this way. In general, P, if you have a smear, a continuous distribution, you can calculate your P by doing the density times each of them has a vector position of your source detail. So this is something we have just talked about with the dipole moment, right? If we have a bunch of them inside the material, so you can look at a material, you have a lot of dipoles like this, P this way, another dipole and P2 this way, and another dipole with P3 this way. So here we have these, what we call dielectric materials. And what do we mean by dielectric? They're not conductors. So they're not conductors. For conductors, your charge are free to move. Your electrons are free to move. So if you have an E field, then the electrons are quickly going to redistribute themselves. But however, with your dielectric materials, your electrons are bound by the protons. It cannot move freely, which means you can see that they can both be influenced by your E field, but you cannot make your charges move freely or have a current running through. So, but they're still trying to realign themselves. For example, if you have an external field pointing up, the positive charges would want to go along with the E field, negative would go against the E field. So they will realign themselves under the external E field, so that you can see this dipole moment P will all be pointing in the same direction as your external E field, right? And we call these dielectric materials. All of these materials like plastic will be dielectric, glass will be dielectric materials. They're not conductors, but they can be polarized, so they can respond to an external field. Okay, so we're going to define a new quantity with which we will describe the polarization. So we're going to call this capital P. And this is defined to be, add up all the little dipoles inside. Each of them have a dipole P, right? We add all of them up and divide it by the volume. So this will tell us the dipole moment of this material per volume. And that's the definition of a polarization of the material. So you can see it is related to the dipole moment, is the dipole moment per volume, per unit volume. Okay. All right, so with that, I'm going to go ahead. We can apply this definition we learned for polarization and do a calculation over here. Give you a sphere, it has a uniform polarization. Polarization is uniform, it's P naught. Okay, can you give me the total dipole moment of the sphere given the P? I'm gonna let you go ahead and vote here. Okay, let's run it for another 10 seconds. If you haven't voted already, please vote. Okay, any last minute vote? Okay, if not, I'm going to end this. All right. Okay, very good. You can see that it is simply a direct application on the definition for polarization. Here, the polarization is P naught. In terms of its magnitude, is going to be the dipole moment, the sum of the dipole moment over volume. So given P naught, we want to find the dipole moment. So it's going to be the sum of your little dipoles inside is going to be the polarization, which is already given, times the total volume of the sphere. So very good, C is correct. You're simply going to put 4 pi over 3 times radius cubed for volume, and you can get your total dipole moment, right? So the reason that we define a polarization so that we're able to relate to sort of describe the strengths of all of these dipole moments, we're interested in the potential it produces. So if you have mostly neutral materials, so what can we do with this information? For a lot of cases, if you have some material and it's neutral, then you know the total charge is 0, right? It does not carry any extra amount of net charge, and charge density is also 0, okay? Because the total charge is 0, charge density is total charge over volume, it's also 0. So if we're interested in the material that's been polarized, what kind of potential it produces, then we can, you just did the multiple expansion method not so long ago. This one says, well, if you're interested in the potential outside, the monopole term for this neutral material certainly vanishes because it does not carry any extra charge. The leading term would be the dipole term, which the potential produced by a dipole is P dot into R over 4 pi epsilon naught over R squared. Okay? So we can use this to calculate the potential produced by a material that is being polarized. So let's look at a material right here. Have a blob of material. And we are going to focus on a small chunk of this, a small chunk of source, which is located at R prime. And each of them are located at a different location. So I'm just going to call this one an R little r subscript, okay? And this little chunk has a polarization, a dipole moment, Pi. And you're interested in evaluating the potential here at this point in space. So in the field, point here, and curly R points from your source to your field, and this is your script dot. Okay. All right. So how do we calculate V due to this little chunk of material, and this little chunk carry dipole moment? So the V produced by this particular dipole is going to be Pi dot into R over 4 pi epsilon R squared. Okay. Then we are going to relate this dipole moment with polarization because we just defined a polarization. For a polarization P, capital P, is the sum of little p's, the total P over volume. So that P dipole moment is polarization times the entire volume. But if I'm looking at a little p, right, a little chunk is going to be the polarization times little d tau. So previously in this problem, you can see the dipole moment, the total dipole moment is your p times the total volume. Here I'm only looking at a small chunk of volume, right? And this volume is d tau. So the dipole moment that is coming from this little chunk is polarization times d tau, a small chunk of charge. Okay, so I can plug this P into my equation to calculate what is the potential produced by this little chunk. So V produced by this little chunk is going to be polarization d tau So to avoid confusion, I'm going to put a little detail behind in the back. So this is not a dot product, okay? Because this is a scalar and the vector is carried by the P. So detail over here, and you instead of using P dot into R, you're going to have polarization dot into R and detail over 4 pi epsilon naught R squared. Now, if you want to know the V total of the entire material, you simply have to integrate it, right? So the V total is going to be the integration of P polarization script R d tau over 4 pi epsilon naught R squared. So this is total. This is D of the little chunk. Maybe I should call it dV. Okay, so this is the equation you have just derived. Given a material, and if they tell you the polarization feature of this material, you can simply plug into the equation to calculate the potential due to such a polarization outside. And in your textbook, it also goes through some proof. If you check Griffiths, so we're not going to do the proofs today in class, but if you check your textbook 4.2.1, it shows that this can be rewritten in terms of two other terms. So we're going to rewrite our potential using two other terms. The reason we do that is these two other terms have some physical meaning associated with it. So it's much easier for us to remember and to make sense out of it. So if we go through the derivation and show that this potential that's written like this can be written in two other terms. The first term is going to be a surface integral between some new quantity, and I'll define what this new quantity means. It's going to be some surface density times the area over script r, plus a second term is going to be a volume integral. And you're going to introduce another new quantity. Again, I'll explain what that means in a second here, over r. So that this sigma b is defined to be polarization dot into n hat. And this density rho b, little b, is defined to be the negative divergence of your polarization. Okay, so that's what these two terms mean. Okay, so starting from here, you can have polarization right here, but I'm going to define two new quantities. One is the polarization on the surface dot into the surface vector. That gives you a new quantity. We call that surface charge. And the divergence of the polarization gives you a new quantity, and we call that volume charge. Okay, so this is normal component of your polarization at a surface. And this is the negative of the divergence of your polarization. And you might wonder why one is called surface density and one is called volume density, and that's what we're going to do next. We're going to evaluate these two terms and see how can we make sense of these two different densities. So it looks as if the potentially produced by this polarization is some contribution for some surface charge, and we call these bound surface charge. And it can also have some contribution from some bound volume charge. Okay. So we are going to evaluate and investigate these two terms coming next. So let's start with, let's say I have a material. I'm going to start a new page here. I have this material. And with surface area A and height D, I'm going to start with this material. And I have to add polarization. After you polarize the material, it may look something like this. Okay, so you have shifted the positive charges away from the negative charges. You polarize it, meaning that you have stretched the positive and negative by a certain distance. So that's what you do by polarization. Okay. Now each of these little molecules have a dipole moment. So each this little molecule now became a dipole with the dipole moment P as QD. So D here is the separation of the charge in one particle, how far away they are from each other. So what will happen is I can show this slides, hopefully that will show you the process of this polarization is before you polarize this is your material. overall it's neutral. It's not neutral, it doesn't mean it doesn't have any charges. It's simply just telling you the total amount of positive charges and total amount of negative charges are going to be equal, so that the overall, so you can see this is overall neutral. And also if you evaluate any little chunk, it's still uniformly neutral within. So the density is 0, right? If you look at the density within some area, the positive and negative are uniformly distributed. So overall you have 0 density, because that's what we mean by Q is 0, rho is 0. Now apply some external E field. You can see these positive and negatives are going to be shifted a little bit. So this is showing that they're shifted by a little bit, right? And the next slide showing the process a little bit more shifted. Eventually they become like this. Okay? So you can see that what is happening is the extra charge is only living on the surface here and here. Within the material itself, you still have that 0 density. Okay. So this is corresponding to a uniform polarization. You are going to end up with just the surface bound charge and on the top and the bottom surface, but within the volume itself is still going to be 0 charge density. The top surface is going to have a negative sigma, and the bottom surface now have a positive sigma. Okay, now let's see if we can calculate how big the sigma is, how much charge density that is. Okay, right, going back. So how big is the sigma? So sigma on the top is going to be, in terms of the definition of the charge density, is going to be total charge, right, divided by surface area. So that's what surface density means. Okay, so charge on top divided by area. The charge on top, if you are going to calculate it, is going to be the number of atoms, and each of them are going to carry the total charge Q over area. Okay. There is also something interesting you can do to this, is instead of writing area, okay, I'm going to replace area by volume divided by the height, D. So this really becomes 1 over area, becomes D over volume, okay? And you may probably already notice what I'm trying to do. So there is a difference, there is a relationship between surface density and volume density. So let's go ahead and look at this question. Here you have a thin slab with the area A and height D. Okay? So this is how we define the volume density, and this is how we define the surface density. Because it is so thin, we're able to think about this as if all the charges are concentrated just on the surface. Okay, so you can express this charge distribution using either a volume density or a surface density. So how do you relate rho and sigma together given this distribution and this diagram? Okay, I'm gonna get you have a discussion about this for a minute or two, and we can go ahead and discuss it together and come back. Okay, all right. Okay, 10 more seconds. Let's finish our vote in 10 more seconds. Okay, all right. Let's take a look at this together. Yes, so choice B is correct. Very good. You can see that if you divide V by A, you simply get the thickness of the slab, which is D, right? So you can relate sigma and roll together like this. So you can see that sigma is rho times D. So you can also see from a previous derivation that the total number of atoms times Q is your total charge, right? Q total. So if Q divided by volume is your density, is simply your density rho. So sigma is rho times D. Okay. If you also want to represent this using number densities, so number density is the number of charge carriers per unit volume. Per unit volume. You can represent this using n. This is n times times the volume is total number of the atoms. So this total number of atoms is going to be n times volume. This volume here is A times D, right? So it becomes A n AD times Q times is the total charge. Sorry, this is the total charge. Let me just write it out. It's n times A times Q, and this is number density n. So sigma is rho times D, which is total charge over total volume, is n Q D. All right, so we calculate the surface density, and previously we're saying how surface density is represented by polarization, right? So this is what we define. So let's look like what the polarization is supposed to be. So polarization P is defined to be all of the little sum of the P's, the dipole moment over volume. And each of the dipole moment is QD, right? Q separated by distance D. And if you add up all the dipoles, which means you have a total number of dipoles, which is number density times volume, gives you total number, divided by volume. Okay, so you can see that I have derived polarization is number density times Q times D. And is exactly equal to my surface density. So here you can see that sigma is equal to polarization P. So that's why we defined, but P is a vector, right? So we're going to look at the normal component of the P, normal to the surface. Because if your P is not normal to the surface, something like this is N. We're going to look at the normal component, the cosine of P to be, that is equal to sigma. Okay, so here sigma will be P times cosine theta, which is the dot product between P and N. Okay, so here we put physical meanings onto the effect of the polarization. So what is the polarization really doing? So as you can see with the animation, what polarization is doing this stretch. So you end up with some bound surface charge on the top and the bottom. And the surface density is related to how much your the strength of your polarization, which is exactly equal to P, or when P is not perpendicular to the surface, is the dot product between P and your surface vector n hat. So if you look at any of the surface in between, so if you look at a random surface in here, right? When you have a polarization, it looks like if you have some charge passing through it throughout the bulk. Let me go ahead and write it here. Have a little polarization going on. So the bulk will get a Q because a Q will enter this bulk, passing through it due to polarization. But Q leaving is equal to Q entering. There is no impact everywhere else except at the surface. Because the surface, you can only either, the charge arrive to the top surface, it cannot go any further. So the top surface, you end up with some bound current density, and the bottom surface will end up with a negative amount of that bound surface current density. The sigma B bound is P dot into N, and we call those bound surface density, surface charge. Okay, so that is the effect of having polarization. We mathematically, we rewrite the potential terms into two other terms, and it looks like the first term is due to the surface charge density. Okay, it's over here. Sorry, this term. This is our first term. All right, now let's look at our second term. Surface charge density only deals with the top and the bottom, and we have just said throughout the bulk, we're not going to end up with anything. But that's not always the case. If your P is uniform, if your polarization P is uniform, then the situation is very simple. Your sigma is equal to P and rho is equal to 0. Okay. However, if your polarization varies, different places have different polarization, then you can see that throughout the bulk is no longer volume, is no longer uniform, right? The positive and negative charges are no longer all mixed together. This part may be polarized more and this part polarized less. So you can see that throughout the bulk, you should have some kind of charge distribution, should have some density. So it gets interesting when P is no longer uniform. So locally, if you look at a local area, you have some charge entering the region, but may not equal to the total charge leaving the region. So how do we calculate the effectiveness of that? So if I look at this entire volume over here, and if I'm looking at this little area, dA, we had just calculated sigma is Q over area, which is P dot into N hat. And here I'm going to use divergence theorem, which states that if I look at the surface integration of P dot into N hat over some surface, this is equal to the divergence of P over the volume, tau. Okay, so this is a divergence theorem. So what is happening is, yes, we're saying polarization, right? So you have this amount of charge leaving the surface, right? It's been polarized, it's been shifted upward. So this is looking at, okay, sigma times A is the charge. So this is the charge leaving the area or the leaving the volume. So it is equal to this quantity. So you can see that if I have one charge, let's call this 20 microcoulomb, for example, exaggerating. If I have this amount of charge leaving this area, so the leftover area after this guy leaves is going to be what, negative 20 microcoulomb, because before it's all neutral. If this leaves, leaving whatever the material left over is going to be negative of that amount of charge. So you can see that if the charge leaving the area, which means after polarization, you should get the volume. So after polarization, you find that your volume has lost this much of charge because it has left. Your volume lost this much charge, okay? And because that is equal to the divergence of P, so you can claim I have lost this much charge. So you can say my lost charge due to polarization is equal to the volume integral of the divergence of polarization times d tau. So if you have lost this much, if you lost 20 microcoulomb, so what you have left is going to be negative of that lost charge, right? So you can see that due to polarization, your material is now picking up a charge of negative volume divergence of P times d tau. So this volume has a negative charge, and that amount of negative charge is given by this expression. Okay, so we can write that using our volume density. So the volume density, the negative charge, if we rewrite it using density, is going to be the total charge is now you have gained in your volume divided by your volume. And you can see if I divide the volume over here, I get rid of my integral. This is going to be negative divergence of P. And we call that bound volume charge. Density. You can see it only show up when you have a non-uniform polarization. But if your polarization is uniform, you can see it's not going to have any divergence, and therefore you're not going to have any bulk density throughout the volume, right? So going back to this animation, this looks very uniform. But imagine if you have more polarization over here, that they are stretched out like this, but very little polarization over here. Then you can see throughout the bulk is no longer, rho is no longer 0, okay? And that effect is described by the divergence of polarization P. So that's why we artificially broke down the polarization process into 2 different terms, because now we have physical meaning of those terms. The first term is simply the normal component of your polarization gives you the bound surface density. But if your polarization is non-uniform, you're going to have volume density throughout the bulk of the material, which is given by the negative divergence of your polarization. Okay, so here, hopefully we have understand the meaning of these 2 terms. One is bound surface density, the other is bound volume density. The reason I say bound, because they are not free charges, right? These are charges due to polarization. It's not like you have some free charges that are free to move. They're not free to move, they're bound. Okay, hopefully let's look at another example. Maybe this will help clarify a few things. Given such a charge distribution, you have such a polarization going on. Looking at this particular case, what do you think about the surface density, and what do you think about the volume density for this case? Okay. What about the bound sigma? What about the bound rho? Are they 0 or non-zero? All right, let's go for 10 more seconds. All right, let's take a look at this. I'm going to close it. All right, here you can see you have some dipoles, little dipoles within your material. And by showing the dipole moment, each of them are pointing upward. So by looking at this, would you claim that you have a uniform polarization? Is P uniform in this case?
Yeah, I would say yes.
Yes, it is. Very good. Everywhere you have the same amount of polarization. So what will happen is leaving throughout the bulk of the material, because the polarization is so uniform, it's still going to have a very neutral and no charge density. Okay? Or you can say divergence of P is now 0, so that your density is going to be 0 as well. Okay. However, you do have some bound charges here on the surface. If you're only looking at the top and bottom surface, you're still going to have bound surface density. So we're going to choose D, which is correct. All right, so now we have another example. We have a dielectric slab with top area A and height H. It's been polarized. As you can see, the polarization is uniform. It's a constant P naught. It's pointing in the Z direction. All right, what is the surface charge density at the bottom surface? Okay. Let's go ahead and vote on this. All right, 10 more seconds and then let's take a look. 10 more seconds. Okay, any last minute vote? All right, if not, I'm going to end this. Okay, here is the result. So how do we go ahead and calculate the surface charge density given such a polarization? What do we do? Said surface density is defined to be what? P that into n hat. So does this mean it is just going to be P naught then? Is that right? So nobody voted for P naught. For those of you who voted for P naught, it's you voted for P, negative. So where is the negative sign coming from?
From the fact that your total charge is no negative charges, or the charge on the surface on the bottom should be negative.
Charge on the bottom should be negative. Very good. You can think of this by looking at, okay, the effect of such a polarization. You must have it external like this. So you can think of your positive charges are being stretched up and negative are left on the bottom, right? Or pushed down to the bottom. So you can see your negative charges should be on the bottom. Or you can see this from your dot product. Your n hat for a bottom surface is down, right? Your n hat for top surface is up. So if P is up and n hat is down, so you're going to have a negative sign, right? So that's why it's negative P naught. Very good. We're not going to choose these because you can see in terms of the magnitude, your density and your polarization are the same. They have the same unit, okay? So you don't have to multiply that by the volume, because if you multiply polarization by the volume, you're getting dipole moment. And we're not asking about the dipole moment. We're asking about the charge density. And surface density is equal to polarization, but not the dipole moment. Okay? So correct answer is B. So very interesting that we have learned the dielectric materials in 1520. So if we have simply giving a E external outside like this, which is E times Z hat in the Z direction. For example, if you insert such a dielectric material inside a capacitor, right, you simply insert in between the parallel plates, you end up with sigma B, which is, if this is P naught, positive P naught on top, and sigma B bottom is negative P naught on the bottom. So you have something like this. P naught, negative P naught, top and bottom. So you can see the field produced by such a polarization. You have positive on the top plate, negative on the bottom surface. You'll end up having E field going down, right? So this is your polarization field. Or you can say this is induced in a way. So new field is going to be sigma over epsilon naught pointing downward, right? This is we know from Gauss's law. It's going to be P naught over sigma in a negative Z direction. So the total E field inside this dielectric material is your E external plus your E mu, which is E in the Z hat plus P naught over epsilon naught Z hat. You can see the new field cancel out part of the external field inside. So make the total field inside the dielectric material a little bit smaller than your external field, right? When this is a capacitor, now when this is a conductor, if this had been a conductor, this new field could 100% cancel your external field, leaving the total field inside the conductor is zero, right? Because E field is always zero inside the conductors, because the charges are free to move. However, for dielectric material, the charges are not free to move. So the result is that you're partially canceling out the E field, but not completely. Okay, so E field is a little bit weaker in the dielectric materials. That's why we also try to sometimes insert material in our capacitors, right? By reducing the E field inside the material, you're avoiding the possibility of having a breakdown. You're able to increase the capacity of storing more energy in the capacitors. Right. So this is the first example we are looking at. And let's look at another example. This example is on a sphere. Again, uniform, it's very uniform, pointing upward. You polarize this sphere with the polarization P not pointing in the z hat direction. So in this case, can you calculate the surface charge density? It's not asking for the bound because if this is uniform, we know the bound volume density is 0 because this is uniform, right? You're not going to have any divergence, but we have a non-zero bound surface density. So in this case, what do you think the surface density is? I'm going to let you discuss this one for a minute or two, and then we can all come together for a discussion. Okay, 10 more seconds. All right, let's take a look. Here are our results. Okay, very good. So we're looking at the dot product between polarization, which is pointing upward in the z direction, and n hat. So for n hat, for a sphere, is really in the what direction? In the radial direction, right? Radial component. So it's really just going to be r hat direction. So the angle between them is measured in spherical coordinates, going to be the angle measured down from the z. That is your azimuthal angle, which is theta. So you can see that, okay, if the dot product between this and this, the angle between them is theta. So you are going to get a cosine theta, right? So which is correctly described by choice D. You're going to end up with some constant times cosine theta. Okay, if you're looking at this using polarization, you may think, oh, that does not look familiar. But that is exactly an example you have already seen in chapter 3. So it is example 3.9 in your textbook. It's a classic example of if you have an external field pointing this way, right? Your polarization this way, and you put a sphere inside an external field, and what is going on inside. So we just see the bound charges are equal to P dot into N, is P naught cosine theta. Okay, so for a cosine, for a constant times cosine theta, you can see that you're going to end up with positive charges on the top and negative charges on the bottom. And if you go back and look at your textbook 3.9, they tell you the surface density is K cosine theta, constant cosine theta. So you can see that that is the exact same problem, right? And you can use the results from before and borrow the results. All you need to do is replace everywhere there's a K with that constant, with now our new constant is P naught, the polarization P naught. So previously in the textbook, we have solved V outside of the sphere and V inside the sphere. So V inside was K over 3 epsilon naught R cosine theta. And now our results is going to be simply K, replace K with P over 3 epsilon naught R cosine theta. The outside used to be K R cubed over 3 epsilon naught 1 over R squared cosine theta. And you can see that we can borrow this result to replace K with P naught, and that is our V for outside. Okay. What's more interesting is to get E from the V. What we can do, I don't have time to do all of that, but I'll outline the rest of this for you, is we're able to calculate our E inside and outside. ER is going to be negative dV dr. D theta, remember we kind of did this before, is 1 over R dV d theta. And this one becomes 2 P naught R cosine theta over 3 epsilon naught R cubed. And E theta is going to be P naught R cubed sine theta over 3 epsilon naught R to the power of 2. All right, so this is for E field outside. If you look at the E field, sorry, not a circle. It looks like this. You can plot this. Something like this. And you see E is not continuous at the boundary, right? E field, E parallel is always continuous. This is something you have seen. But E perpendicular component, this is perpendicular E field, doesn't have to be continuous. And they above the obey such a boundary conditions as E above minus E below. We call this is sigma over epsilon naught. Right, you probably remember this from dv dn above minus dv dn below is negative sigma over epsilon naught. So this one we use a lot for chapter 3 and boundary conditions, right? It comes from the E. So here E is not continuous because E is perpendicular to the boundary and there's some surface charge here at the boundary. What you can do is you can plug in your E outside, and you can plug your E below and apply it at the boundary, and indeed they are equal to the surface charge density. Okay, so that little part I don't have time to solve, but I could include that part in my notes. All right, so that's all I have to say for polarization. We do chapter 4, and kind of quickly we will spend another lecture time on displacement. We will also do chapter 6 a little bit quickly so that we can have a little bit time to do chapter 7. So sorry about the mix up in your grades. I will go through everything one more time and I'll fix it all and I'll send you an update on that, okay? Now, if you see a problem, again, if you haven't told me already, let me know so I can, when I fix everything, I can make sure that is addressed. Send me an email, okay? All right, I'll see you guys all on Wednesday. Bye, everyone.
Thank you.
Thanks, Dr. Ryan.
Bye-bye. Thank you.
Hey, Dr. Ryan,
Yes.
when you did the example, it was above, it had like a, I think it was a cube, and the answer was minus P naught. I don't understand where that answer came from. Do you think you can?
For this guy?
Yes.
Oh, the minus sign come from this. This is the surface. For a bottom surface, this surface N is pointing outward, down.
Right.
So P is up and N is down. So that's why you have a negative sign when you do dot product.
But what about the top part?
Top surface,
Isn't that-
its N hat is up. So top surface positive, bottom surface negative.
So why do we only care about the bottom surface?
Oh, it's just asking the bottom surface. We care about both. top-
Oh, okay, I didn't see that. Okay,
No problem.
thank you.
Okay.